Hey guys, welcome to video 44. Today we're going to start talking about metal oxide semiconductor field effect transistors, otherwise known as MOSFETs. And in particular, we're going to be talking about enhancement mode MOSFETs, which are the most commonly used in analog and digital applications. They come in two varieties, N-channel and P-channel, and just like BJTs and JFETs, you're going to see way more N-channel devices used, so that's what we're going to concentrate on. In the center of the page, we've got the cross-section for an N-channel enhancement mode MOSFET, and it's very similar in structure to an NPN BJT, except that the control terminal, the gate, is not directly connected to the P region in the center, but rather it's insulated by a very thin layer of silicon dioxide. And the idea behind how it works is that when we apply a positive VGS, because this insulating region is so thin, we're going to create a very strong electric field between the gate and this P region. And at a relatively low voltage, this field will create an inversion layer in the P region. That is a region that behaves like N-type silicon, and it creates a conductive channel between the drain and the source. The minimum voltage required to create this channel is called the threshold voltage or turn-on voltage, and we'll talk about that more in a second. But the greater VGS is above the threshold voltage, the deeper this inversion layer penetrates and the greater the drain current can be. So what we've got again is a voltage controlled current source, much like a BJT or a JFET. Now the transconductance for this device is given by I sub D equals K times VGS, the applied bias, minus V sub TO, the turn-on voltage or threshold voltage. Now I'm using V sub TO to represent this voltage because I use V sub TH to represent Thevenin voltage and V sub T to represent thermal voltage. So we'll use V sub TO in this discussion to represent the threshold voltage. K is just a proportionality constant, and we'll talk about that more later. The graph of the transconductance equation is parabolic, as we see here. The vertex of the parabola is the turn-on or threshold voltage. And the drain curves are very similar to those that we would get for the collector of a BJT or the drain of a JFET. And the saturation region, what we would typically call the active region, is separated from the ohmic region by the transconductance curve, which is transposed down here in green. All right, and by the way, I usually refer to this region where the curves flatten as the active region. It's also called the saturation region because that's when the conductive channel between the drain and source is saturated. And likewise for a JFET, the conductive channel is also saturated in this region, unlike a BJT where saturation is over on the left-hand side. This is the saturation region for the FET, and this is called the ohmic region because in this region the drain current is more or less linearly related to VDS and VGS. And we'll talk about that more in other applications as well. Before we move on, I want to mention this substrate terminal here. This connection is required in order to get the P region at a voltage relative to the gate. In other words, it allows us to actually establish a potential difference that's meaningful between the gate and this P region. So generally the substrate is connected to the source terminal, and we treat this as a three-terminal device. In some cases the substrate is also called the body terminal, and in integrated circuit applications, it's generally connected to the most negative point in the circuit. But for a discrete device like this, we just connect it right to the source and treat this as a normal three-terminal device. All right, so let's just move on and take a look at a couple of actual enhancement mode MOSFETs. So what we've got here is some data for two very common MOSFETs, the BS170 and the 2N7000. These are virtually identical electrically, at least on paper, and the only difference between them is the pinouts. for their packages. On the left-hand side here, we've got the schematic symbol, and notice there's a diode connected from drain to source. This is what's called a parasitic diode. It's formed during the fabrication of the MOSFET, and since it's reverse biased under normal conditions, we're just going to ignore it. Now, if we come down here to the typical transconductance curves, notice right off the bat that the drain current range they're giving is extremely high compared to what we're going to be using it for. Remember, we're using this as a small signal amplifier, so we're going to be biasing it up down here in the low milliamp range. So these curves are not really too useful to us, although we are going to use them right now to determine this proportionality constant K. What we're going to do is pick a convenient point, and I chose where all the curves intersect, and that's at 4 volts, and it gives us about 0.33 amps of drain current. So we'll solve this equation for K, and that gives us K equals I sub D divided by VGS minus V sub TO squared. Using our values here, we've got 0.33 amps divided by 4 volts minus we'll use the typical value, 2.1 volts squared, and let's see what that gives us for K. All right, so we've got 0.33 divided by 4 minus 2.1 squared equals about 0.091. I'm going to round that to 0.1. Okay, so we've got a K value of about 0.1 amps per volt squared. Okay, so we're going to use that in all of our future analysis. Okay, but before we go on and look deeper into the transconductance equation and so on, one thing I want you to notice about these curves is that at higher current levels, as temperature goes up, drain current decreases. This is the opposite of what happens for bipolar transistors. When you're operating them at high current levels and high temperatures, when temperature goes up, collector current goes up. And remember, that can cause what's called thermal runaway. We've discussed that previously. Enhancement mode MOSFETs work the opposite. As temperature goes up, the drain current goes down. So this is an inherently self-power limiting device, and that is very advantageous in applications like, say, audio power amplifiers for your car, where if the amplifier is sitting in the trunk, baking in the sun, we don't want thermal runaway to happen. So MOSFETs are, very, very advantageous in applications like that. They tend to be very thermally stable, and that's why they're very popular now in high power amplifier applications. All right, now let's look at the drain curves for a second here, and notice that they're also given for relatively high current values, and we're going to be operating way down here. So again, these curves are not too useful to us, but that's not going to be too much of a problem, as we'll see in a moment. Okay, so let's move on to the next slide. All right, I grabbed a whole bunch of random BS170s and 2N7000s and sat down in the lab and made some measurements and plotted my own transconductance curves for low drain currents, and this is what I came up with. I got an effective threshold voltage of about 1.5 volts, and K still came out to be about 0.1 amps per volt squared. And so I'm going to use these values in our upcoming analysis problems. Okay, but before we move on, just to show you the pinouts for these devices, the BS170, looking at it from the flat side on front, goes drain, gate, source, versus the 2N7000, which interchanges the source and drain. It's source, gate, drain. So be aware of that when you're building circuits. If you swap them out, you have to flip them around. All right, now let's apply these values and see what we come up with for some practical circuits. All right, we'll start with the simplest biasing arrangement, that is fixed gate biasing. It's also the least likely to be used because it's very sensitive to parameter variations. But it is simple. So what we've got is a voltage divider, and the drop across R2, the Thevenin voltage, is VGS. Remember, because we're looking at basically an infinite gate resistance, we're not going to load down the divider at all. So we don't need to worry about loading effects here. All right, we're going to determine the drop on R2, which is VGS, back substitute into the drain current equation, and we've got our answer. And because it's so simple, let's just go do a couple examples. All right, in example number 1, we've got a 2N7000, K equals 0.1, threshold voltage is 1.5 volts. So let's find VGS, and that is VGS equals VTH, which is VDD times R2 over R1 plus R2. Call up our calculator. R2 is 220K divided by 1 meg plus 220K would be 1220, and times 10 volts is 1.8 volts. So our VGS is 1.8 volts. Drain current we find just by substituting into ID equals K times VGS minus VTO squared. All right, K is 0.1, VGS is 1.8 volts, VTO is 1.5 volts squared. Let's see what we come up with here. Okay, 1.8 minus 1.5 is 0.3 squared times 0.1 would be 9 milliamps. Okay, so what we've got is ID equals 9 milliamps. VDS is going to equal VDD minus IDRD, right? So ID 9 milliamps times 330 ohms, that's going to be pretty darn close to 3 volts, okay? You can verify that, but I'm just going to say this is going to be approximately 3 volts, and that means our VDS is going to be about 7 volts, okay? So there we go. We've got 9 milliamps drain current, VDS is about 7 volts, VGS is 1.8, and we're good to go. All right, next example, the same transistor, but now we're determining R2 and R sub D to give us 2 milliamps drain current and 5 volts for VDS. Let's start by finding RD first. That's a little bit easier, okay? So we got 5 volts dropped across the transistor. That leaves us 7 volts dropped across RD with 2 milliamps. That means R sub D equals 7 volts divided by 2 milliamps, and what is that? 7 divided by 0.002 is 3.5 k ohms. All right, now that's not a standard value, so we'd either use 3.3 k or 3.9 k, whichever was more convenient. All right, but I'm just going to assume for the sake of argument that we do have 3.5 k ohms here. All right, so let's go ahead now and determine what value R2 needs to have. All right, so we need 2 milliamps drain current. So what we're going to have to do is figure out the needed VGS to get that. So we know I sub D equals K times VGS minus VTO squared, and we're going to have to solve this for VGS. All right, so we've got ID over K, and we're going to take the square root, and what we're going to end up with is VGS equals the square root of I sub D over K plus V sub TO, and that's what we need dropped across R2 to turn this transistor on appropriately. So what we've got is 2 milliamps, 0.002 divided by 0.1 plus 1.5 volts. Let's see what we get here. All right, so 0.002 divided by 0.1, we'll take the square root, plus 1.5 means we need a VGS of about 1.64 volts. Okay, so I'm going to write that over here, 1.64 volts. All right, and now we're going to have to solve the voltage divider equation for R2. So let's clear out our workspace, and we know that VGS or VTH equals VDD times R2 over R1 plus R2. We're going to solve that for R2. All right, so VTH over VDD equals R2 over R1 plus R2. I'm going to invert both sides to make this easier to work with. You'll see why in a second. So VDD over VTH equals R1 plus R2 over R2. And now I can split this into two fractions because I've got a common denominator. That's equal to R1 over R2 plus 1, R2 over R2. All right, and I want to get R2, so let's subtract 1 from both sides, and we get VDD over VTH minus 1 equals R1 over R2. So R2 is equal to R1 divided by VDD over VTH minus 1. Let's plug those in and see what we come up with, okay? So VDD, oops, let's drag that out of the way. VDD is 12 divided by 1.64. 12 divided by 1.64 minus 1. Okay, we'll take the reciprocal and multiply that by R1, which is 1 meg. And we get about 158.3 k ohms. All right, so 158.3 k ohms. That's not a standard value, so the closest standard value is about 150k. I don't know that that's going to work too well, but we could give it a shot. We'd like to use 158.3 if possible. So we could trim this with a potentiometer or something, but unfortunately it doesn't work out to a standard value, and that happens. So, you know, we just have to work around it. But there's two examples of fixed gate biasing. It's not very practical, but it is relatively simple. All right, so what we're going to do next is take a look at a little more commonly used biasing arrangement, and it's less sensitive to parameter variations, but requires a little bit of preparation to understand how it works. So let's go on. So what we've got now is, again, voltage divider biasing, but we've added an external source resistance, RS, this time. So this is sort of equivalent to adding an emitter resistor to a BJT voltage divider biased circuit. All right, over here we've got the Thevenin equivalent, and because the gate current is essentially 0, we're not going to have any voltage drop across the Thevenin resistance. All right, so writing a KVL equation for this loop here, KVL, we get 0 equals VTH minus VGS minus ID times RS, okay? And we're going to solve this equation for VGS. We got VGS equals VTH minus ID times RS. And then we're going to back substitute that into our transconductance equation, I sub D equals K times VGS minus V sub TO squared. All right, so we're going to substitute in VTH minus IDRS for VGS. That gives us I sub D equals K times VTH minus I sub D times RS minus V sub TO, the quantity squared. Now, what we're going to have to do is expand this out, and since we've got 3 terms, we're going to get 9 terms here in the expansion. Then we're going to substitute that into the quadratic formula, and we'll get 2 solutions. One will be our actual drain current, the other will be extraneous. And I'm not going to drag you through all the algebra involved in doing this. I think you can see it would be pretty long and tedious. But what I've done is worked it out ahead of time and come up with the nice equations for you. And how about I just drag those over right now, okay? So here's what we end up with. And let me pull those over here and we'll talk about this, okay? So what we've got is the quadratic formula. A is equal to K times RS squared. Okay, K is our proportionality constant for the MOSFET. B is equal to 2K times the threshold voltage times RS minus 2K VTH times RS minus 1. And C is another big, long, messy constant as well. These get evaluated, plugged into the quadratic formula, and there we go. We're going to use the solution where we're subtracting, okay? And I'll show you why that's the case in a little bit, but I'll normally calculate both roots just for the heck of it, but remember, we're going to use the subtracted radical here for our actual solution, okay? So this is kind of messy. It's very error prone. Probably the best thing to do with this would be to either write some kind of script in, say, Excel, or if you have a programmable calculator, you can just enter your constants and have it crunch it ahead of time, because this is very messy to evaluate manually. But anyway, let's just go ahead and take a look at an example problem, okay? All right, our circuit uses a 2N7000. We've got an RS of 150 ohms, and the first thing we want to do is evaluate VTH. All right, so we've got VTH equals VDD times R2 over R1 plus R2, and that gives us 270 divided by 1270 equals times 15 volts. So we've got a VTH of about 3.19 volts, okay? 3.19 volts. And then we go ahead and evaluate the constants for the quadratic formula A, B, and C. The only one I remember off the top of my head is A, and I know that's equal to K times RS squared. So let's see what that is, just for the heck of it here. Let's see, RS is 150 squared times 0.1 is 2,250. 2,250. Now, when you're calculating these coefficients, you're going to come up with all kinds of big and small numbers, and it's hard to tell which ones are sensitive to small changes or not. So what I recommend is when you calculate these values, just take them out to the full precision of your calculator and go with them, okay? Because again, it's hard to say which ones are sensitive to very small changes or not at this point. So what I want you to do right now is pause and evaluate these coefficients, plug them in the quadratic formula, and determine these circuit values, okay? And now that you've done that, I'm going to go over and get my results. Okay, and here's what we've got. Okay, let me grab these, pull them over, and we'll talk about what we see here. Okay, so of course we calculated VTH previously. That's 3.19 volts. A was 2,250. B works out to be negative 51.7. And constant C is 0.28561. When we substitute these into the quadratic formula, this is what we get. And our extraneous solution is 13.7 milliamps. Our actual drain current is 9.2 milliamps. So let me write that here, 9.2 milliamps. And VDS works out to be 4.42. It's VDD minus ID times RD plus RS. In other words, 15 volts minus this drop, okay? And we're going to come out with 4.42 volts. And finally, VGS, one way to find it is VTH minus ID times RS, and that's 1.81 volts. Now, we can also evaluate this graphically by using something like Desmos, and I've got that up here. So let me open up my browser here and show you what we've got. Now, here's my transconductance equation. This is K times VGS, which is X, minus VTO, the turn on or threshold voltage squared. So that's our parabola. And this equation, 3.19 minus X over 150, that's VTH minus X divided by RS. Okay, that gives us the line for the drop across RS. And we can see our solution is 9.24 milliamps. And the extraneous solution, 13.7, just like we predicted. Okay, 13.7 and 9.2. Now, really, the proof that this is all worth doing is actually building the circuit and seeing if it works correctly. And I did that. I built this circuit, used about 10 different MOSFETs, 5 different BS, now I forget the part number, BS 120s and 2N7000s, and I ended up with, for the 2N7000s, I got about 9.4 milliamps every time, and with the BS 150s, I ended up with about 8.2 to 8.3 milliamps each time. So the parameters that I derived earlier for this MOSFET are pretty well right on the money. Okay, so what I recommend is, if you've got some of them handy, go ahead and breadboard this circuit and make some measurements, and I think you'll find out that these numbers are pretty much right on the money. All right, so let's do another example. All right, here's our circuit. This time it's a design example. We're going to use a 9-volt battery to power the circuit, and we need to choose the source resistor and drain resistor to give us ID of 2 milliamps with a VDS of about 4 volts. All right, first things first, let's find the Thevenin voltage here, and that's VTH equals VDD times R2 over R1 plus R2. All right, see what we come up with here. 470 divided by 1470 equals times 9 volts is about 2.88 volts. So our VTH is about 2.88 volts. I'm going to write that over here, 2.88 volts. And the next thing we want to do is find the required VGS to establish 2 milliamps drain current. So we're going to solve the drain current equation, ID equals K VGS minus VTO squared. For VGS, again, we've already done this, and we know that VGS is equal to the square root of I sub D over K plus V sub TO. So that's the square root of 2 milliamps divided by 0.1 plus 1.5 volts. And let's see what that comes out to be. Clear 0.002 divided by 0.1 square root plus 1.5 gives us 1.64 volts. So we need VGS equal to 1.64 volts in order to get 2 milliamps. Okay, so let me write that in here. 1.64 volts. That's a little messy. And now we can determine the source resistor because we can do KVL around here that says this drop, ID times RS, is equal to VTH minus VGS. So that's 2.88 volts minus 1.64 volts. And that drop is, let's see, clear 2.88 minus 1.64 is 1.24 volts. So we need to drop 1.24 volts across RS. That means RS by Ohm's law is 1.24 volts divided by 2 milliamps, and let's see what we've got here. 1.24 divided by 0.002, 620 ohms. All right, so if we could, we'd use a 620 ohm resistor here, but that's not a standard value. The next closest values are what, 680 ohms or 560 ohms. Okay, so if I went with 680, I'd get a little less than 2 milliamps. If I go with 560, I'll get a little more than 2 milliamps. I'm going to go with 680. Okay, so let's set RS equal to 680 ohms. It'll give us slightly less than 2 milliamps. All right, next thing, let's determine R sub D. So let's see, what is our drop here? We've got 9 volts minus 4 volts minus 1.24. So 9 minus 4 minus 1.24 is 3.76. So we're going to want to drop about 3.76 volts here. So RD is equal to 3.76 volts divided by 2 milliamps. Let's see what we come up with. 3.76 divided by 0.002 is about 1.8 k ohms. That's a standard value. I like that. 1.8 k ohms. And I like when that happens. Doesn't happen nearly enough. So 1.8 k ohms. And there's our design. 680 ohms for RS, 1.8 k for RD, and we should get about 4 volts across the MOSFET with 2 milliamps. Okay, now of course I built this circuit just to verify that all this work was worth the effort, and for the 2N7000s using a 680 ohm source resistor, I got consistent drain currents of 1.8 milliamps. Okay, that was ID. And I did this with about 7 or 8 different devices. They all came up at 1.8 milliamps. And then the BS170s that I tried, BS170s, all came up at around 1.5 milliamps to 1.6 milliamps. So apparently the BS170s have a slightly smaller K value than the 2N7000s, but you couldn't tell that by looking at the data sheets. But based on my results, that's the case. And if you try this, maybe let me know how your results come out. Now, you guys know that I would not leave you with this messy work that I've done here, so I'm going to bring over a condensed version of this material for you in case you want to do a screen capture. And here it is. Okay, let's get that a little closer. And here you go. Okay, so we've got one more biasing arrangement to look at, and we're almost at the end of the video. So let's move on to the next slide. The last biasing arrangement we're going to look at is shown here. This is drain feedback biasing. It's somewhat similar to collector feedback biasing we talked about with BJTs. So let's take a look at the circuit, and one thing we're going to notice is that since we have 0 gate current, the drop across RF is 0 volts. And that means that our drain to gate voltage is also 0 volts. So VDS is equal to VGS for this circuit. Okay, and again, we would derive some parameters to use the quadratic formula to solve for the drain current here, and I've already done that ahead of time. They're very similar to the ones that we obtained for voltage divider biasing with a source resistor, except instead of RS we've got R sub D in the equations, and instead of VTH we've got VDD. All right, you can verify that by expanding out the equations and going through all the algebraic reductions, but trust me, this is what it comes out to. And if there's anyone that actually wants to see the derivations, let me know and I'll make a video showing all these derivations step by step if you'd like. But for right now, we're just going to use the results that I derived without all of the pain involved in the minutia getting there. All right, so let's just do an example or two with this biasing arrangement and see what we come up with. Okay, so here's example 5. We're using a 2N7000 again, so we know that K equals 0.1 and V sub TO equals 1.5 volts. All right, and let's go ahead and do the analysis of this one. Okay, so we know A is equal to K times RD squared, and again, that's the only one I can remember, but let's see what that comes out to here. All right, so we've got RD is 2000 squared times 0.1 is 400,000. Okay, so remember I said you're going to end up with all kinds of huge and small numbers for these constants, and here's an example of a pretty big one. The rest of them are calculated similarly, but let me just go ahead and drag those over for you. Okay, if you want, you can pause right now and calculate them yourself, but here's what I ended up with in my results. Okay, so let's pull this over, and what we end up with is, again, A equals 400,000, B equals negative 5,401, and C equals 18.225. All right, plugging these into the quadratic formula, we get a drain current of either 6.9 milliamps or 6.7 milliamps. Now, these solutions are very close together, but 6.7 is the correct one. We're again using the minus sign here. We're doing negative B minus the radical, okay? And VDS, which is equal to VGS, is VDD minus IDRD, 1.6 volts. So we've got VGS is 1.6 volts. I sub D is 6.7 milliamps, and VDS is 1.6 volts as well. And we can verify this one using Desmos just like we did previously. Let me pull that up. We've got our transconductance equation here, so what we'd have to do is modify our ID times RD line here. Okay, so we're going to put VDD up here instead of VTH, and VDD was 15 volts. Our drain resistor goes in place of RS, and that's 2,000 ohms. And here is our line, and now you can see why those two solutions are very similar. Our correct solution is 6.621. We said it was 6.7, pretty darn close. And 6.9 versus 6.881. So I rounded a little bit, but in any case, this is our solution, and that's how you could do it graphically on Desmos. Okay, this is VDD minus X over RD. Okay, so let's do one last example, and we're almost done for the day. For this last example, we're going to do another design problem. We've got a 9-volt battery powering our circuit. We've got a 2N7000, so that means that our K is 0.1 and V sub TO is about 1.5 volts. All right, and remember VGS equals VDS in this circuit, so whatever we've got for VGS, that's what we'll have here. And what we need to do is just determine VGS required to give us 2 milliamps, right? So again, we're going to solve the drain current equation for VGS, and we've done that a couple times. We know VGS equals the square root of I sub D over K plus V sub TO. So again, we've got the square root of 2 milliamps divided by K, which is 0.1, plus 1.5 volts. A little messy again, and let's see what we come out with here. We've got 0.002 divided by 0.1 square root plus 1.5 is about 1.64 volts. So we require 1.64 volts, and that's also going to be VDS, 1.64 volts. So now we can find the drop across R sub D, which is going to be 9 volts minus 1.64. So we've got 9 minus 1.64, which is 7.36 volts. 7.36 volts. So using Ohm's law, R sub D equals 7.36 volts divided by 2 milliamps, and let's see what we've got here. 3.68K, 3.7K if that was a standard value. The closest standard value is about 3.9K, so that's what I'd go with here, 3.9K ohms, and that would get us pretty close. And what I recommend is that you guys either build the circuit or check the Desmos solution and see how close it comes out using 3.9K ohms. Now, I did build this circuit just like all the others, and I tried it with a number of 2N7000s, and I got drain currents consistently of 1.9 milliamps, and with the BS170s, the drain currents came out consistently at 1.8 milliamps. So that's a good indication that these parameters are very good estimates for these devices. Now, before we wrap it up completely for the day, I decided that I would write down the derivations for the constants that go into the quadratic formulas. I did it in whiteboard because it's a little bit easier to write on than paint. And here's what we've got. We see the expansion of the 3-term quadratic into 9 terms, simplification, and finally at the end, we've got our 3 coefficients, A, B, and C. And I also did the derivation for the drain feedback version, and here it is. It's basically the same operation. We expand it out, and we've got VDD in place of VTH and R sub D in place of R sub S, and that's really the main difference that shakes out of this whole thing. So there you go. Those are the derivations. Hopefully you can make sense out of that. And like I said, I could go through them step by step sometime if there's anybody that wants to see that. All right, and that concludes today's video. I hope it was enjoyable. I liked making it, and hopefully it was something useful to you as well. Next time we'll probably talk about MOSFET amplifiers, and we're also going to do depletion mode MOSFETs one of these days too. So I'll see you guys next time around.